so we're jumping into Unit 5, which is all about kinetics. Kinetics, as just like how thermodynamics was really, really important, kinetics is also very, very important for the AP test, as well as just like chemistry. So we're going to be talking about rates and differential rate laws today. A lot of this stuff is going to line up with calculus, so if you are in calculus, you might understand some of this, or you will understand it after doing some more stuff in calculus. I don't know if Math 3 aligns with it. When I was in school, we didn't have like Math 1, 2, and 3, so I have no idea what the situation with that is, but this is a lot of calculus with integrals and differentiation, stuff like that. So, jumping right into it. Kinetics, the study of reaction rates. So we're going to be looking at how fast reactions happen. The rate of a reaction can be viewed three different ways. The rate of disappearance of a reactant, so we can look at how fast the reactant is going away. We can look at the rate of appearance of a product, so we can look at how fast a product is appearing or being made. Or we can look at the rate at which the overall reaction proceeds. So we're just going to look at the entire thing as it goes. All reaction rates are found by looking at the change in concentration over a period of time. So we're looking at the rate in relation to the concentration. When the concentration is lowering, that means it's going away. If its concentration is getting bigger, that means we're getting more of it. All right, so this presentation is a little bit longer, but it can go by pretty quick. So kinetics, jumping right into it. So we have our basic equation, A plus B yields D plus E. And you're going to see this a lot. The rate of disappearance of a single reactant. So we can look at how much a reactant goes away. And what we're going to do is we're going to do the rate is equal to negative. The negative sign is needed as the rates are always positive values. And this negative value is going to make the change in the concentration of A positive value, because we can't have a negative rate. It's not going to run backwards. It's always going to run forwards. So the change in A, the change in the concentration of A, so this bracket that you see right here, that means concentration. So if you see a bracket with a compound in it or a variable, for instance, that means the concentration of that compound. So we're looking at the change and the concentration of A over the change in time. Little t is time. And we're going to put that negative in front of it if we're using a reactant A or B. We can look at the change or the rate of appearance of a single product. So if we're doing the product side, so like D, the rate for compound D is equal to the change in the concentration of D over the change in time. Very, very simple. The rate at which one species appears or disappears can be used to find other rates. So if we know A, we can find B or D or E. So we're going to take 1 over the coefficient of whatever you're looking at, let's say A. So we're going to take 1 over the coefficient times that rate. So the negative change in the concentration of A over delta T, or change in time. And that's going to be equal to 1 over the coefficient for another one times that one's rate. And that can be equal all across the board. So we're looking at a specific reaction in this case. So 2NO2 yields 2NO plus O2. And they're just looking at that rate. So over time, the concentration for NO very rapidly increases in the beginning. And when we get to this point, well, whatever, back up. So it rapidly increases, but is steadily going to level off. So that's going to be your, I forget what that one's called, exponential growth. And in calculus, we can find instantaneous rates, and that's just the slope at a specific point. You can take the instantaneous rate at any point, but they took it right here. And you can figure out what the rate is at that given moment, which is when you take the concentration and the change in time. or you can take it from here, and it'll be a different concentration and a different time, but it will also have a different rate. For the specific equation, the concentration change for NO2 is a exponential decay, whereas NO is an exponential growth, and they are opposites of each other but the same rate. Opposites concentration-wise. O2 is being produced at half of that rate, because it just is. The instantaneous rate is equal to the negative slope of tangent for reactions. Tangent just means a straight line that touches one single point on the curved line. So looking at this, 2AB yields A2 plus B2. So over here we have AB, 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 a bunch of ABs. We have 2 moles of that. It says that AB's molarity, or concentration, is 15 molar. And it says that at this time, at T equals 0, A's concentration is 0 and B's concentration is 0. When we move over here, we have A2 and we have B2. And that's at time equals 60 seconds. At this point, AB's concentration is 5, and A's concentration is 5, and B's concentration is 5. So basically it kind of like spread out, and we could calculate any of these numbers using the ones that we have. If like B was X, we could calculate what that is based on everything else. So we can calculate the rate of disappearance of AB. So the rate is equal to, so we're looking at the disappearance of AB, so it's going to be, since we're doing reactants, we have to do the negative. The change in the concentration, so from AB to AB on the other side to the product side, our change is actually 10 molar. And over time, that's over 60 seconds. And if you do the math, you get 1/6. And that change was actually a negative number, which makes it positive overall. You get 1/6, molar per second. The rate of appearance of A2, so the rate equals, and since we're doing a product, we don't have to do the negative sign, so it's just going to be the change in the concentration of A2, which is 5 minus 0, minus 60 seconds again. And this 5 is our product concentration, and this 0 is our reactant concentration for that. And do the math there, 5 over 60, 1 over 30. Same thing. So moving down, differential rate laws. Differential rate laws express the relationship between the concentration of the reactants and the rate of the reaction. So now we're going to be looking at the concentration and the rate together. The differential rate law is usually just called the rate law because it's the normal one. Integrated rate laws express the relationship between concentrations of reactants and time. So now we're going to be looking at time with that. So the rate law, the rate of the overall reaction, has its own equation where K is the rate constant specific to a certain reaction at a certain temperature. They will give you that constant. M is the reaction order in terms of A, and N is the reaction order in terms of B, and you will learn how to figure that out here in a minute. So reaction orders M and N. Reaction orders cannot be predicted from the balanced equation. They are found through experimental data, and they will probably give that to you as a given. So reaction orders can be either zero order, first order, or second order. Those are your 3 choices. So M and N can either be 0, 1, or 2. Or you can have multiple, like you can have both of them be 2 or both of them be 1, but those are your only choices. So for zero order reactions. Alright, so for zero order reactions, if we double the concentration, there is no effect on the rate. So basically for zero order, we put that 0 as the superscript, and the rate is equal to K times the concentration of A to the 0 power, which is just 1. So the rate is only equal to K on zero order reactions. If we double that concentration, it's still going to be K. So there's no change to the rate if we double that concentration. For first order reactions, doubling the concentration doubles the rate. So the rate is equal to K times the concentration of A to the 1 power, which is just the rate equals K times the concentration of A, or they're saying X here. If we double that concentration, 2 times the concentration of A, it's still to the 1 power, so your rate is actually 2 times that value. And for second order reactions, when we double the concentration, it actually quadruples the rate of the reaction because the concentration of A is squared here, giving us this rate equals K times X squared. Doubling it quadruples the rate because it was already, doubling the concentration gives us this 2x value if we're doubling that concentration, but it's squared also. So it's squared and that 2 squares to get you 4. So we're actually going to quadruple that rate if we double the concentration in a second order reaction. So overall order for a reaction, to find the overall order of the reaction, you simply just add those exponents. M plus N gives you the overall order for that reaction. So these are the units for K, the rate constant. So for zero order reactions, these are the basic formulas, and these are the orders. So for a zero order reaction, your rate is equal to K, and the units for K are molar per second. If it's first order, then the units are just 1 over seconds. If it's second order, then it's 1 over molar seconds. And if it's third order, then it's 1 over molar squared times seconds, which is super complicated. But whatever, you have to roll with it. So when we're writing a differential rate law, the problem, write the rate law, determine the value of the rate constant K, and the overall order for the following reaction. So we're given this reaction right here. And we need to figure out, first of all, we need to write the rate law, and we need to determine the value of the rate constant K. But first of all, we really honestly need to figure out what the orders are. So, part 1, determine the values for the exponents in the rate law. We need to figure out X and Y, or M and N, as they have said before. So what we do is we look at, so we need to find 2 instances separately. The first instance is we need to find where one of our compounds stays the same in concentration, but the other one is going to double. That's the key. We need to figure out where one of the compounds doubles in concentration, but one of them stays the same. So we're only looking at one of them. So in this case, Cl stays the same, but NO doubles. And after we look at that, we look at the rate. What happens to the rate when the concentration doubles? Well, in this case, the rate quadrupled, which means that NO is in the second order. Then, after that, we jump to a different scenario in the same problem. It's the exact same graph, chart thing. But this time, NO is staying constant, and we're looking at Cl when it doubles. This time, we look at the rate, and we see that the rate doubles. This means that the reaction is first order. So there's like a little 1 right there. Next, determine the value for K, the rate constant, by using any set of experimental data. So we just pick one of them, because in any one of those experiments, we have a concentration of both of them and the rate. So all we're missing is K in this case. So they picked experiment 1, they put the rate in right there, and they put in the 2 concentrations with the order as its exponent. And then they calculated K to be this value. Part 3, determine the overall order for the reaction. All they did was just add up the exponents. 2 plus 1, the overall order for the reaction is 3. This is the third order. Example number 2. 3 experiments were conducted at a specific temperature for the following reaction. We get these 3 experiments. Find A, the rate law, B, the rate constant at this temperature, and C, the overall order. So, first thing we do is we figure out what our exponents are. So this is the same thing. Yes. So, from experiment 2 to experiment 1, let me see if I can make this easier. So right here, well, they're doing this first. So they're doing experiment 2 and 1, and they're saying during this time, NO doubles from 2 to 1, but from 2 to 1, H2 stays the same. So what we do is we say what happens to the rate during this time, and doing it on my calculator, 0.0225 divided by 0.09. Oopsie, I think I did that backwards. 0.09 divided by 0.0225, and it actually quadruples. It's times 4. So my exponent for NO is actually a 2. It's second order. Now let's look at another set of data. It says from experiment 3 to experiment 2, from 3 to 2, my NO stays the same, but my H2 changes. Now it doesn't double. So what they're saying on this slide is that you can kind of do some math in there. Let's see. So in this case, the H2 actually goes up by 1.5, and also our rate multiplies by 1.5. And from there I can just say that it is basically 1. The rate is equal to the change in that concentration, so I call that first order. From there, you can find, what is it asking for? The rate constant, and we can plug that in. So we can just pick one of the sets of data, and we can say any rate that we pick, let's just do experiment 3, 0.015 equals K, which is what we're trying to find, times the concentration of NO, which they said was 0.1, and that's squared, times H2's concentration, 0.2, and that's to the 1 power. You do all that math, and you'll just get K. And I just don't want to do it, because I'm on my phone. Alright, so spectroscopy. Spectroscopy is a pretty large part of chemistry in college. Up until my senior year, I was doing spectroscopy. So it's a method of analysis which is based upon the absorbance of electromagnetic radiation by matter. So basically, you put an aqueous solution in a little cube, and we put it in this spectrometer, and it shoots light through it, and then it records the data of the frequency and wavelength that's coming through, that's able to get through. So we're able to record the intensity of the electromagnetic radiation, and that's going to be equal to the intensity of the exciting sample plus the intensity of the radiation absorbed by the sample, and that's how you get the intensity of the entire sample. The intensity of the stuff coming in is equal to the stuff that's in here that's being absorbed plus the stuff that's going out, which makes sense. We use Beer's law when doing spectroscopy a lot because we need to get different concentrations. Beer's law is really easy to use. So basically, our absorbance is equal to molar absorptivity, which they will give you that number, times the path length, that's just how long it is, how long that cylinder or cube is, times the concentration, which they make C in this case. And that's how you can figure out your absorbance numbers. So example number 3, rate law. It ties right into rates. 3 experiments were conducted at 25 degrees Celsius for the following reaction, which occurred in a 1 centimeter cuvette. The cuvette is like the little cube that you put the sample in, and it's 1 centimeter long. That's your path length. So B plus C yields D plus E. B and C are both 0.1 molar right here. We have a different concentration here and a different concentration here. And this is what the absorbance looks like with those different concentrations over time, the same amount of time. And it wants us to find the rate law and the rate constant at this temperature. So what we do, so we're looking for So the first thing that we need to do for this is find little a for the colored reactant. So what we're going to do is the colored reactant is the C. And what we can do is we can just pick one of these, and we can just pick this one. And we can do big A, which is the absorbance, which we can find. We'll just use we'll use 60 seconds. Or we'll use 120 seconds because that is really close right there. So big A is 0.25 equals little a, which we're trying to find, times B, which is our path length, which we can leave in centimeters, 1 centimeter, times our concentration, which is 0.1 molar. And from there, you can just do some really, really simple math and get your little a. So the good news about Beer's law is that the absorbance, which is our capital A right here, is mostly proportional to concentration. It is proportional to concentration. So basically we can say that this y-axis is concentration. And the easiest way to find the initial rate is by calculating the slope at that line, at that one point right in the beginning. That's going to be our easiest way to do it. Either that, or from there, we can, let's see. Yeah, the best thing I could say would be to use the slope of that, that curve for each one to find the initial rate. Next thing they do is they make a chart with each of the 3 experiments, the concentrations, and the initial rates of each of those. Oopsie. And then from there, step 4, they do the same thing that we were doing before, comparing this one to this one. And then from 1 to 2, from 1 to 2, C doubles. So what happens to its rate? It also doubles, which means that we have a order of 1. It's first order. And then, what's the word? I can't think of the word. Whatever. For the other one, oh goodness. For the other one, we can look at the other 2 experiments from 2 to 3. Oh, no, we can't. We're going to have to look at 1 to 3 because that's when C stays the same but B changes. And that also makes the reaction double, so it's also first order. So from there, we can find the rate law. We have the concentrations for each one. We have the rate for the experiment, and each one is first order, and you can find K very, very easily. And that will be it. If you have additional questions about how to calculate this stuff, you can come ask me. Homework and book help will be very helpful in this case, but there is more to come. Tomorrow is integrated rate laws, which will be even more kinetics.